All right, let's get started. A lot to go through today about probability distributions for discrete random variables. So let's quickly go through the disclosure that an employee of Columbia develops Stan, manager of LLC, uses Stan, creates a conflict of interest. Someone posted a private message on Piazza saying they were thinking about this class or one class in the business school, and we're concerned that maybe this is all fake news or something like that. If it makes you feel any better, basically all of the professors in the social sciences are doing something related to their research, earning more than $5,000 per year. However, you just sort of do it as a consultant and there's no actual product involved, then somehow that's different than if you make software available for free to download. So I don't think it's actually that big a deal, but I got to say it anyway. Also, Piazza still have more people enrolled in the class than registered on Piazza to take part in the discussions, which constitute 1/6 of the grade. So we're still missing some people who haven't even logged in at all. Some people who have managed to log in but not clicked on any of the posts to read them. So it's difficult to make a contribution to the discussion in that situation. Of course, if you clicked on the post, you would find that there's not all that many. So the rest of you are not really doing enough to move the discussion along. And, we're not going to have time in class to address absolutely everything. There've been a few posts on Piazza that are pretty good, although tending to look, more forward for the rest of the semester than what we've done so far. But you need to get in the habit of asking questions when you don't understand, because we're moving through this stuff really quickly, answering each other's questions from a Bayesian perspective, questioning each other's answers of other people's questions. It's a whole mindset that you have to get into in terms of thinking in terms of how can we communicate with probability distributions, what are the uncertainty involved, how will we go about making a decision in this or that research situation that comes up over and over again if you start training yourself to look for these sorts of things. Finally, there's a poll on Piazza. A number of people have voted, a number of people who haven't. That's actually okay if you're not planning to attend. But if you are planning to attend, the poll will close at 6 p.m. today. So get your vote in for the preferred times Monday morning quickly. Last I looked, it was a very close race. Might have to go to a recount, but we'll see. Get your votes in. Questions about that? Questions about anything from last time? I did.
How much later should we show up on Monday if we're not doing the car?
Oh, yeah. So basically about halfway through, we'll probably switch from like R stuff to review stuff. But anyway, it'll only be like an hour. Okay. So Tuesday, we started to talk about the Bernoulli distribution, which is a distribution over the sample space 0, 1, where 0 represents failure, 1 represents success. And these functions that we've been talking about have a special name. They're called probability mass functions in the case where the random variable is discrete, some function that inputs a value of the random variable from the sample space, any parameters. In this case, we have 1, which is pi. It's a probability. So it is forced to be in the continuous 0 to 1 interval, including the endpoints. Anyway, if you input those two things, evaluate it, you get back the probability that this random variable takes the value little x. Little x can be either 0 or 1, given this probability pi. And the probability mass function for the Bernoulli distribution can be written as pi raised to the power of x multiplied by 1 minus pi raised to the power 1 minus x. And so once you have the probability mass function, it's a relatively straightforward thing to evaluate the expectation of that that random variable, or some expectation of a function of that random variable. So in the case of just, the simple, what is the expectation of a Bernoulli random variable? We apply the definition. We take each element of the sample space, multiply by its corresponding probability, sum it up over the entire sample space. In this case, we get 0 times the probability of failure plus 1 times the probability of success, and that just evaluates to pi. So the expectation of a Bernoulli random variable is pi, the probability of success. And then we can go on to evaluate the expectation of some function of a Bernoulli random variable, such as the function x minus pi quantity squared. Of course, the expectation of that function is special. It's known as the variance, and we learned on Tuesday that there's a shortcut for calculating the variance. It's the expectation of the square minus the square of the expectation for the random variable you're talking about. And in the case of a Bernoulli, x squared is equal to x because the only values it can take are 0 and 1. 0 squared is 0, 1 squared is 1. So expectation of x squared is the same thing as the expectation of x, which we just said was pi. Then we subtract off the square of the expectation. That can be written as pi minus pi squared, or more commonly, pi times the quantity 1 minus pi. So the variance of a Bernoulli random variable is pi times the quantity 1 minus pi. And that may seem like a very simple distribution, and it is, but it's one that applies a lot in the social sciences, where we have an outcome variable that's either success or failure. You don't vote or you do vote, or something like that. Where we're interested in these pi's, but more specifically, we're interested in some function of the predictors that generates pi. So in the case of a logit model, we parameterize the pi in the Bernoulli probability mass function as 1 divided by 1 plus e raised to the power negative alpha minus beta times some predictor z. We can do that for each of the n observations in our data set, and that's basically the essence of a logit model for a 0-1 outcome, which you're probably already familiar with from some of the other classes that you've taken. But this, we're going to approach it in a maybe more consistent with the probability theory approach to it, in which case we would be wanting the posterior distribution of alpha and beta given the data that we have. So Bernoulli distribution is at the heart of logit models. We'll get to more, tons of regression models toward the middle of the semester, but is there any questions about the Bernoulli distribution or how we came up with the expectation of the variance? Shoot. Right. So x can only be 0 or 1. So 0 squared is 0, and 1 squared is 1. So in this case, x squared is the same as x, and so the expectation of x squared is the same as the expectation of x. That's special to the Bernoulli distribution, but it's true. Andres.
That's a good question, but notation-wise, why are you using pi?
That's more common in the case of Bernoulli, but none of these distributions have like universal notation. For the most part, if we're talking about a simple expectation, this would be called mu. But a lot of times when people talk about probabilities, they want to use an ancient Greek letter that starts with the same sound as probability. So they use pi because iota doesn't sound like probability. Believe.
A little bit confused by the notation or like the letters used in the last sentence. So for the nth observation, so I will talk actually about just one observation.
Yes. So each observation may have a different predictor: your age, your income, your gender, your race, etc. And so the probability of voting from one person to the next differs because they have different values of the predictors. But for each person, you have some probability of voting. And, you know, we're putting a linear function there. But yes, certainly you can say, you know, pi is the same for a whole group of people, or you can say everybody has a different pi, depending on how you want to model it. Other questions? Okay. Binomial distribution extends from the Bernoulli because a binomial random variable is defined as the sum of n independent Bernoulli random variables that each have the same probability of success, pi. So if that is the sort of definition of a binomial random variable, what would be the sample space for a binomial random variable? Marlon.
Instead of positive integers.
Not quite.
Plus 0.
Okay, we want to include 0, but it's not all non-negative integers. Up to n, right? So 0, 1, 2, up to n. If n is 1, then the binomial and the Bernoulli are the same thing. But if n is more than 1, then the binomial and the Bernoulli are different, although related, and so the sample space is 0 to n. So what would be the expression for the expectation of a binomial random variable? Correct. So we learned last time the expectation of a sum is equal to the sum of the expectations. And what did we say was the expectation of a Bernoulli? So pi plus pi plus pi n times would be just n times pi. Everybody understand how we did that? Okay. What would be an expression for the variance of a binomial random variable? Well, what did we learn last time about the variance of a sum? Salif?
That depends on if they are dependent or independent. Okay, so say they are independent. So otherwise, if they were not independent, we have to add also the twice their covariance.
All right. So if these were dependent, there would be, you know, variance plus twice the covariance of all pairs of these n variables. But because the definition of binomial presumes the Bernoullis are independent, if they're independent, they have 0 covariance. So 2 times 0 is all 0. We can forget about the pairs of covariance between all of these and just sum up the n variances. And in this case, the n variances are going to be the same. Pi times 1 minus pi. So the variance of a binomial random variable is n times pi times 1 minus pi. But the assumption that they're independent is very important and indeed baked into the definition of a binomial random variable. Got it? So how could we come up with an expression for the probability mass function of a binomial random variable? Let's say n is 3. So we're adding up just 3 Bernoulli random variables and trying to get up the probability mass function that it's 0, 1, 2, 3, 4 values in the sample space. But as a hint, I'm giving you there's 8 cases that you have to consider when coming up with a unified expression for the probability that x is, whatever, given the success probability pi and the fact that it's 3 Bernoullis that we're adding up. So let's think about that for a second. Maybe more than a second. Marlon.
Over x times pi of x 1 minus pi of minus x.
Somewhat close. How did you arrive at that?
Give the number of ways we can get 3, 1, 0. Get from the
Yeah, okay. I think you're on the right track here, but let's just sort of spell it out specifically. So 2 of the cases are all 3 of them succeed. And since they're independent, that would just be pi cubed. And then another case, all 3 of them fail, which would be 1 minus pi quantity cubed. So that's 2 of our 8 cases. What are the other 6 cases that we have to worry about? Good, almost. Now, so we might have the case, okay, 1 succeeds and 2 fails, right? But how many ways are there for that to happen? Great. So let's say like these 3 people down here are my Bernoullis. Nathan, number 1 could succeed. Andres and Shubing, is that right? Could fail. Or Nathan and Shubing could fail and Andres could succeed. Or Shubing could succeed and Nathan and Andres could fail. So there's 3 ways that could happen. And there's 3 ways for 2 to succeed and 1 to fail. Just if we switch this up. So there's 8 cases to consider in all when saying how we're going to specify this. And so we could write a piecewise function, but it turns out we don't really need to write a piecewise function because the general definition of a probability mass function for a Bernoulli random variable is this right here. N choose x. The n choose x function is defined as n factorial divided by x factorial divided by n minus x factorial. That basically gives the number of ways in which there could be x successes and n minus x failures when order is not being considered to be important here. And then we have the rest of it, which involves pi raised to the power x, the number of successes, multiplied by 1 minus pi, which is the probability of failure, raised to the power number of failures, n minus x. That includes the special case where x is equal to 0 or x is equal to n. So the choose function involves factorial. Everyone familiar with factorial? And just remember that 0 factorial is defined to be 1, again, in that edge case. So think about the binomial distribution and its probability mass function is you have to take into account the number of ways in which you can get x successes and n minus x failures. So it's basically just using your you know, general addition rule and stuff like that to come up with a concise formula for this function. Questions about how we came up with that? Okay, bowling again. So why, you might say, well, could we use a binomial distribution with n equal 10 to help model the first roll of a frame of bowling, but why would that be inappropriate?
Drawing a ball at pins, obviously, they're not independent of each other.
Right. So the way in which the pins are configured in space, you know, if one in the front gets knocked down, the probability that the ones behind it get knocked down is going to be, you know, higher. So it's not the case that like the front pin is independent from the next pin or anything like that. So the assumption of independence here basically works against us there. Could we use the Bernoulli distribution for the probability of success in, or the probability of being successful, having some probability of achieving a strike on the first roll of a frame of bowling? Would that make sense?
Yeah.
Yeah? We can maybe allow the probability to differ from one person to the next? Possible, sure. Okay. Could we use the Bernoulli distribution for the probability of knocking down the pin in front? Have like a triangle configuration to them?
Well, if you're only thinking about the first roll.
Yes. Right. Should have said first roll. That makes sense? Sure. Okay. So we define a random variable x is just the indicator function, or xi is the indicator function that the ith pin is knocked down, and pi I is the probability of doing so in a Bernoulli distribution. And then what concept is illustrated by this expression here, the probability of knocking down, or, you know, knocking down the first pin given the probability of doing so, multiplied by the product from 2 to 10, the probability of knocking down the ith pin given the ith probability, and the previous realizations of x up to I minus 1. So let's think about this just in the case where I is 2. So we have probability of knocking down the second pin given the second pi and whatever x1 was. So we have probability of knocking down the first pin multiplied by probability of knocking down the second pin given that the first pin either was or was not knocked down. So what are those two things together tell us? The joint probability of what happens to the first two pins. So they could both get knocked over, both not get knocked over, the first one but not the second one but not the first. So the, you know, I equal 2 covers us for the first two pins. And then for I equal 3, probability of knocking down the third pin given pi 3, and what happens to the first two pins. So we have marginal times conditional of 2 given 1 times conditional of 3 given 2 and 1. So what's that? Right. Joint probability distribution over the first 3 pins. And if we roll it up all the way to 10, then this expression gives us a complicated but valid this one's a marginal, but the whole thing together? Joint probability distribution over what happens to all 10 pins. So, you know, the binomial distribution, assuming that they're independent, not appropriate for bowling. 10 different Bernoulli distributions where you explicitly take into account the conditioning of one given all the ones previous. Maybe, or certainly valid, but maybe a useful way to come up with a joint probability distribution for what happens on the first roll of a frame of bowling. So the problem here with binomial is the independence. But if we construct dependent Bernoullis, then, you know, now we have something that might make sense. But this is going to involve, you know, a ton of different conditions, you know, for the 10th, given what happens on the 9th and the 8th, 7th, all the way up to the first pin. So there's going to be like 2 to the 9th things to think about when modeling the probability that the 10th pin falls down. So complicated, but a good use of the general multiplication rule. Okay. So one of the limitations of binomial is that it assumes n is fixed, is like part of your research design. And even though the binomial distribution is not appropriate for bowling, at least in bowling, 10 pins is fixed. It's part of the rules. But a lot of things in social sciences, we don't really have a fixed n or a useful fixed n. So, you know, the number of people who vote in the last election, that's not something that is, you know, fixed. It's part of the Constitution or anything like that. So a lot of times we want to think about, well, what is a distribution over the non-negative integers that doesn't have this limitation that it assumes the parameter n is fixed. And so to get around that, we might think about some limits. So what if n, the number of Bernoullis that get summed up, is allowed to approach infinity? So sequence 8, 9, 10, infinity, etc. But at the same time, we let pi get closer and closer to 0. So n is approaching infinity, pi is approaching 0, but we do the limits in such a way that the product of n and pi, which is the expectation of a binomial random variable, mu, remains fixed. So n is getting bigger, pi is getting smaller, but the product of them is remaining the same. What happens with the binomial probability mass function given here when we do those? So just because this sort of what happens in the limit is, you know, something goes one way or another is a pretty common thing in probability. We'll maybe, you know, do one of these things once, but it basically just involves, you know, some math tricks. So we have this third term over here, 1 minus pi raised to the power n minus x. We'll substitute mu over n for pi. That remains fixed. Then we'll break up this, you know, thing raised to an exponent as 1 minus mu over n raised to the power n multiplied by the quantity 1 minus mu divided by n raised to the power negative x. So all that's legal. The tricky part of this is to recognize, or maybe learn for the first time, that this is actually the definition of e raised to the power negative mu. E is defined as this raised to the power n as n goes to infinity. So this term here goes to e to the negative mu. The other one is easy. So x is fixed. So here we have, fixed thing divided by n is going to infinity. So this third piece is 0. 1 minus 0 is just 1. 1 raised to the power of anything is 1. So here, the limit of this is just e to the negative u. But that basically just means knowing what the definition of e is. It's not merely 2.71. It has a whole limit thing, several actually, that characterize it. Then this other piece, n choose x times pi to the x, we can expand that out. Substitute mu over n for pi, we get this expression here. Then there's just a classic switcheroo. Remove this over here, move the x over there. If you sort of stare at that, as n goes to infinity, all the terms are on the order n. So this piece over here is going to have a limit of 1. And then x and mu are fixed, so that piece doesn't have a limit. We just have this. And so we put those two things together. Under this limiting process, the probability mass function becomes mu to the x, e to the raised to the power negative mu, divided by x factorial. And that is what's known as the probability mass function for the so-called Poisson distribution, whose sample space is the non-negative integers. And the Poisson distribution is a very common distribution in the social sciences for modeling count variables. Not necessarily a great choice, but a common one. And that is one way of motivating the Poisson distribution. Yes?
So you have populations that would have, that are, you're assuming that for each, let's say we're voting for voting, as what we're trying to do. It's assuming that the process that generates for each person, whether vote, is independent. So if one person voting is independent of the other person, except for tricks if they both share, that
so
would in the same population.
Conditional on pi. Right. So the assumption is that these are conditionally independent given each person's probability of voting, which may be the same for some people, but it could be different between old people and young people. So if you're conditioning on age, then you might have a pi for old people and a pi for young people, just to be gross simplification. But yes, this is the limit of a binomial, and binomial consists of n independent Bernoullis, conditionally independent Bernoullis. Becca.
For the very first section there, that as n approaches infinity, I approach 0. In the example of voting, it's also very unlikely that 0 people vote, right? So n is very far from infinity.
Correct.
In that case, but pi is also very close to 0.
So what you're in thinking about the voting thing, you want to focus on mu being fixed, because that's really the thing that you're going to be interested in. And so when we say 66% or something like that of registered voters vote, that is an estimate of mu. And so usually when we're thinking about these sort of things in a Poisson process, it's how does mu change from one group of people to the next. But technically it's saying there's an infinite number of opportunities to vote. Every millisecond you have an opportunity to vote on voting day, but the probability that any one person votes in that millisecond is very small. But there's a lot of milliseconds and a lot of people.
So n is I'm thinking about n in a 2 link.
Yeah. Rashika.
Poisson is supposed to be based binomial distribution, but is it the case that, for example, if you know that approximately the number is supposed to be 100,000, then do you lose accuracy?
Probably not much, but if you sort of literally do a sample of 1,000 people or something like that, and that was part of your grant, then it would be more appropriate to consider in fixed than in asymptotic. Other questions? Nathan, number one?
Maybe way simple, but just to clarify, but in the limit of approaching infinity and the limit of pi approaching 0, such that we're saying that they're doing it in a way that's how mu stays constant.
Yes.
They're moving at the same rate in opposite directions. Okay.
And they're both positive. what would be the variance of a Poisson random variable? Yes? Mu. And how did you arrive at that? And what is your name? Amy. Okay. Amy, how did you arrive at that? You remember it. Do you remember how you arrived at it? Does anyone else remember how Amy arrived at the answer mu? Merlin.
Can we take the variance from binomial? The same. Essentially, we do the same way as we get from the binomial to so on. And that pi goes to 0, the second term becomes 1, and the first term becomes n times I, which is mu.
Right. So we said the variance of a binomial is n times the variance of a Bernoulli. And so if we stick an n right here, and we said n times pi is what? So we got mu, and we got 1 minus pi. But what's happening to pi? So we have mu times 1, which is mu, which is what Amy meant. Questions about that? Okay. So, going back to bowling, it's a little bit of a contrived example, but it's a good opportunity for us to use the Poisson distribution, which we just learned about, and to do something that is more reminiscent of the process that we're going to be doing the rest of the semester when we're applying Bayes' rule. So, little known fact, what we were doing before with using these ratio of Fibonacci's was actually just a special case of a more general distribution that could be used to study bowling that has the probability mass function of knocking down x out of n pins given some unknown parameter gamma. It's the x plus gamma Fibonacci number, so gamma has to be an integer, non-negative integer, divided by negative of the Fibonacci number gamma plus 1 plus the Fibonacci number n plus gamma plus 2, again presuming that n is greater than or equal to x. So gamma can be any non-negative integer, and we're going to assume it has a Poisson distribution, or our beliefs about gamma follow a Poisson distribution. And you can see what we were doing last week is just a special case where we fix gamma to be 0, because the Fibonacci number of 0 plus 1, that's the first Fibonacci number, which is just 1. And we had a negative 1 there before, but we could generalize this, and it's still a valid probability mass function if we let gamma be any non-negative integer. And so you can source in the following code here, which just generalizes our probability function to take into account what gamma is. But you can see if you evaluate this probability function over the entire sample space for any non-negative integer value of gamma, it still sums up to 1. So it's still a valid probability mass function for things like bowling, but it gives us the opportunity to think about doing what we would more ordinarily do, is say, okay, well, we have data on bowling. How can we estimate what a person's gamma is? So we have this unknown gamma that we might like to estimate or think about estimating. About that? Okay, prior predictive distribution. This is a very important concept in Bayesian analysis. Given your beliefs about the unknown gamma, what do you believe is the distribution for the first roll and the second roll of a single frame of bowling? And that might not be something that is immediately obvious or intuitive from a mathematical perspective, but we can easily answer this question. And the answer to this question is known as the prior predictive distribution using simulations involving composition. So we repeat the following 3 steps many times. We draw a realization of gamma, which I denote with tildes, so that means random draw, from a Poisson distribution given mu. And mu is going to be provided by u. It can be any positive real number. It doesn't have to be an integer. And what makes this example kind of contrived is because gamma here is not a really intuitive parameter. You don't have a sense of, you know, like what's a big gamma or what's a small gamma. So it's hard to think about a prior distribution for that or what would be reasonable. But since we've only learned like 2 distributions and one of them is the Poisson, we're just going to go with the Poisson for this one. Loosely speaking, the bigger gamma is, the worse bowler you are. But actually the pins and stuff are not very sensitive to gamma. They're just slightly sensitive to gamma. But you can maybe imagine that there's actually a stronger relationship between gamma and the probability of knocking over pins. But just to simplify, bigger gamma, worse bowler. So we draw a realization of gamma from a Poisson distribution, which represents our beliefs about gamma given some mu that is fixed and provided by u. We then take our realization of gamma and we use it to draw a realization for the first roll of a frame of bowling given gamma and n equals 10. So just, you know, evaluating this function at our realization of gamma for the first roll. And then we use our realization of x1 to draw x2, assuming that, you know, x1 is not 10, from a bowling distribution given our realization of gamma and that there's n minus x1 tilde pins remaining. We can do this simulation process over and over again as many times as we want. And this really represents our model for a person bowling. We don't know what gamma is, but we have beliefs about it. We draw from our beliefs. Given a realization of gamma, we can do the Fibonacci thing to draw the first roll. And given the first roll and a realization of gamma, we can do the Fibonacci thing to draw second roll of a frame of bowling. We understand the basic idea here. And we can implement this in our code using the replicate function. So the replicate function takes a number of times that you want to do replications and an expression, which can be included in curly braces if you want to do more than one of them. And this replicate function is very common, used when you have an expression involving simulation of random variables. So if this didn't involve any simulation, it would just be doing the same thing over and over 10,000 times. But if it's doing the same expressions over and over 10,000 times, but the realizations are different, then we actually get, you know, different simulations. So we draw from a Poisson distribution, which is encoded in the R function RPOIS. In general, the functions in R that start with R indicate I'm drawing a realization from some distribution, and then the suffix on this pertains to what distribution you're drawing from. And then it's basically arbitrary how many letters are in the suffix and how those correspond to the distribution. So just memorize that it's RPOIS, but that is fairly obvious that it pertains to a Poisson distribution. Then we sample x1, create a smaller sample space for the second roll, sample x2 using the probabilities that we used before, and then we just, you know, return back the realizations of these 3 random variables that we can look at And so we've essentially generated predictions for x1 and x2, but the predictions that we have generated take into account our uncertainty about gamma. We don't know exactly what gamma is, and so when making predictions about pins in bowling, we have to propagate our uncertainty about gamma to our uncertainty about the results of what's going to happen on this frame. But all this uncertainty propagation can be summarized very well with a large number of simulations. Another way of thinking about the prior predictive distribution is to emphasize this concept of a generative model, which is a model that you've specified completely enough that you could simulate from it along the lines of the previous slide. And if you don't have a fully specified generative model, you can't use Bayes' rule to update your beliefs about those distributions because you don't have a complete model to begin with. But a lot of people, when they're doing research, they sort of, just jump in halfway through the process and don't really think about the details of all the stuff that is going in the model. Christina, you had a question? That is a good question. Like I said, it's not particularly intuitive, but you might just in general terms say bigger gamma, worse bowler. So gamma might be something like the reciprocal of how big you are. So if you can't even like roll a heavy ball down the thing, you're not going to be very good at bowling. But if you're like a fully grown adult, then maybe so. So it's something like inversely related to skill at bowling, but it's actually the pins are not that sensitive to gamma. They're just like a little bit sensitive to gamma. So it might be something like how bad your eyes are. You can think about it in different ways, but something related to skill at bowling. Salif?
Just to say it in other words, but so basically gamma is something like one of the predictors.
We certainly don't observe data on it, but our model posits the existence of this parameter which discriminates bowling ability from one person to the next. So everybody has their own gamma, and we want to estimate what yours or somebody else's might be with observed data on pins falling down. So in a more maybe educational testing example, you might think of gamma as like intelligence, and intelligence governs how well a student performs on standardized tests. And we want to take your test scores and estimate your gamma.
I'm just confused about what our goal is for this parameter. So we want to get gamma, but we actually want to get the distribution of x1 and x2.
Conventionally, we would want to estimate the distribution of gamma, posterior distribution of gamma. We're not quite there yet, but that's where we're going. There's another question over there, Christina?
Since gamma is related to the number of pins, can it be something like quality of the floor or something?
Yeah, so if it was a property of the floor, then you might think it's the same for everybody who bowls on that lane, and that'd be fine. Or you could think this is like a property of the person, and it differs from one person to the next. Also fine. You were in my class 2 years ago. Stephanie.
Yes.
Okay.
So could you say gamma is just general uncertainty that?
It contributes to the mean as well. So higher gamma, lower mean, but only slightly. And the fact that we don't know it contributes to the uncertainty. Nathan, number one.
When we're doing something like this, gamma is always something that we can't concretely figure out, unlike the different realizations of x1 and x2 between 0 and 10.
Correct. So that's what I mean by the following thing, which basically says when constructing a model, a generative model, you want to put things into 4 buckets, depending on whether they're exogenous or endogenous to the model, and whether they are known or unknowable, or never going to be known for certain. So in this simple thing that we've set up, the exogenous known is mu. That's just going to be a number supplied by you. And in this example, it's going to seem hard to do that because gamma isn't really that intuitive thing. But you're supplying what you expect gamma to be by specifying mu, the expectation of this Poisson distribution. So before you see any data, what you expect gamma to be. The endogenous knowns, which are like things that we could collect data on, but our model is attempting to explain, would be x1 and x2, the number of pins you knock down on the first roll, number of pins you knock down on the second roll. So we can get data on that. That's an observable thing, but we're coming up with a generative model to explain, you know, how many pins get knocked down by this bowler. So it's endogenous to the model, but knowable. Conversely, we have exogenous things that are unknowable, like gamma. We're not attempting to explain where gamma comes from as part of our model. It just gets plopped in. And this is perhaps not the most satisfactory aspect of the model, but I needed to fill up all 4 boxes. Now, although gamma is knowable, we are assuming that you know your beliefs about gamma, which would be a hard thing in this situation because it's kind of abstract. But since we just learned the Poisson distribution, you know that your beliefs about gamma are Poisson with expectation mu, and you can say what mu is. So this x1 and x2 is like collected data that we have already. But the 4th thing, the endogenous unknowables, are future predictions for number of pins knocked down first roll, number of pins knocked down on the second roll by this same bowler, but in the future. So maybe that's not totally unknowable because we could just wait. But as of right now, you know, we don't know what your future rolls are going to be. But, you know, we have a model that gives us predictions of them given a realization of gamma. We could predict your future bowling success and scores and all of that if we had, you know, updated beliefs about gamma. So that is endogenous to the model. We want to explain it. We want to predict it. But it's unknowable because it depends on another unknowable, gamma. Now, when I say it's unknowable, I don't mean that we have like absolutely no information about it. I mean, like what Nathan is saying, we're never going to know it absolutely for sure. But we might have a more concentrated posterior distribution for it. All right. So think about those 4 categories when constructing a model. Another thing that generative models are good for is, you know, all this stuff about specifying prior distributions like that for gamma, especially when you're first starting out. It seems like that would be a really hard thing to do. But the good thing is you can just try something, draw from the prior predictive distribution, and then see if the resulting distribution of x1 and x2 looks reasonable to you. So gamma is not observable, and that makes it seem kind of hard, but pins knocked down are related to gamma, and you might have a more concrete sense is like what would be a more reasonable bowling score. And does, you know, what x1 and x2 corresponds to what I think would be reasonable. If so, then your prior on gamma is probably not that bad. But if, you know, you're predicting like a 2-year-old gets a perfect score on bowling, then you might want to rethink your prior distribution that you're using for gamma. And that happens all the time. Your first priors that you say, okay, I'll just try to do something simple. You draw from the prior predictive distribution and you get these predictions of the outcome that are like, that's impossible. and you kind of go back to the drawing board. Another thing that drawing from the prior predictive distribution is good for is, once you kind of settled on your priors, you can get a realization from the prior predictive distribution, stick it back in to your estimation model, and see if you can recover the realized value of gamma. That helps confirm that your software is working properly before you try it on data from the wild. Nikhil.
For the convergence behavior, the call essentially be asymptotic from analysis for the area?
So conditional on the data, there's all sorts of convergence stuff. But here, where we're not actually conditioning on the data yet, we're just simulating data. These are going to just follow the distributions that we specify in the model. So no, there's no central limit theorem stuff really going on here yet. Other questions? Okay, so let's say we're sort of settled on our generative model. We're happy with our choice of mu. We might get some data like this. This is just 9 frames. The 10th frame in bowling is a little weird, so I'm just say you only observe 9 frames, and they look like this. And then you might say, okay, how can I use this to update my beliefs about gamma? And you do so as follows. So let's say you observe 9 frames. What do you believe about gamma given these data on the previous page? So we want the posterior distribution of gamma given the 2 rolls on 9 frames in our initial expectation for what gamma is represented by mu. So that's the left-hand side of Bayes' rule. The right-hand side, again, follows the formula that we talked about before, but just with different symbols. We have a prior distribution for gamma given mu, which we are saying in this example to be Poisson. We have this generalized Fibonacci ratio bowling distribution thing for pins, first roll, second roll, first frame up to 9th frame, given gamma. Then we have the denominator piece, the probability distribution for all the number of pins knocked down, irrespective of gamma. Those 3 things together, if we can evaluate them, will give us the left-hand side, which is a function that will tell us what we ostensibly want to know. What is a probability distribution for gamma, conditional on the data that we've observed. And usually we would observe a lot more than 9 frames. But just to keep it kind of simple, 9. That's Bayes' rule. So we said this is going to be a Poisson distribution. And this is really all that we did before. Frequentist would be kind of okay with, as long as the probabilities from bowling come from a lot of realizations of a process that you observe. Frequentist will even leave you alone if you just say, I assume the probabilities come from this Fibonacci process. That's okay. But when you start saying, I have beliefs about gamma, instead of saying, I'm going to fix gamma to 0 or 1 or whatever, whenever you say, okay, I'm uncertain about gamma, but I have some probability distribution over it, frequentists say that doesn't make sense. Gamma is a constant. You can't have a probability distribution about a constant even though you don't know what it is. There's no repeated thing that we could do that would just reveal what gamma is. And if there were, it wouldn't change. Gamma would be the same thing every time we do it for a particular person. There's no variation in it. So how can you have a probability distribution about it? And, Bayesians come back and say, well, okay, yeah, gamma is a constant, but we don't know what it is. And my beliefs about gamma follow a distribution like the Poisson distribution. And now I'm just using the rules of probability to give me a coherent way of updating my beliefs about what gamma is in light of the data that's coming in. And at that point, frequentists, not as much today as in the past, but still it's reasonably common to hear them say, well, yeah, mathematically you could do that, but classes like this one shouldn't be offered. And if they are, people like you shouldn't take them, because you should not be wasting your time learning something that shouldn't be used. And for things like science, policy, running a public company, whatever it may be, the analysis and stuff that goes into it should not depend on what the analyst or anyone else believes about gamma. It should only be determined by analyzing properties, functions, whatever, for the data, conditional on the unknown. So there's no Bayes rule or updating, because you shouldn't be injecting your beliefs into the scientific process anyway. Conversely, Bayesians say, well, ultimately we're using science and we're making policy decisions and stuff like that based on this quantitative stuff. It's going to come down to someone making a decision about what to do. And if you're not making decisions to maximize your expected utility, given whatever you think the probabilities are that go into that expected utility, then you're just making stupid decisions. And that's really just the irreconcilable difference between these two approaches to quantitative methods. So we said in this case, we're going to assume that's Poisson. It follows the Poisson PMF. What is second term in the numerator here? Probability, all the pins, given gamma for 9 frames. So let's say, I skipped the 10th frame because it's confusing, but let's just say bowling only has 9 frames. What's the probability distribution for a whole game of bowling given gamma? So how would we write down a function for the number of pins knocked down in the first roll of the first frame, number of pins knocked down in the second roll of the first frame, number of pins knocked down on the first roll of the second frame, number of pins knocked down in the second roll of the second frame, etc., all the way up to number of pins knocked down second roll, 9th frame. What do we have to use to come up for something like that? Robert. And how many probabilities go into each frame?
2, I guess.
1 marginal, 1 conditional? Yeah. So due to the independence of frames, we can get the probability of a whole game by multiplying the probability of each frame together. And within each frame, we have a marginal probability distribution for the first roll based on the generalized bowling Fibonacci thing, and a conditional probability distribution for the second roll, given what happens on the first roll of the nth frame. So we're using general multiplication rule. Some things, like frames, are independent of each other. Some things are not, like rolls within the frame. And so in that case, we have to do marginal times conditional to give us a probability for the nth frame. Multiply those n frame probabilities together, we have a probability function for an entire game minus the 10th frame. Merlin. Well, I just eliminated the 10th frame because sometimes you get an extra roll or two. That was all. Just makes it more complicated. You could still do it. Christina?
Why do you have any equals 10?
Oh, so I used n twice. N equals 10 here. That's the number of pins to start with. But it goes up to 9 frames. So I should have used like I or something for the frame. All right? Just using the rules of probability. Okay. So what then is the denominator piece? The probability of all the pins getting knocked down irrespective of gamma. What do we have to do in order to obtain that? How do we go from joint to marginal? Correct. So there's kind of two ways of looking at this. One is to say the denominator is the expectation of some g function, where the g function is the numerator, or the g function is really this piece on the right-hand side of the numerator. And the weighting distribution we're using is the piece on the left for gamma given here. And so you can see this as the expectation of this function here, which is known as the likelihood function for gamma. This function is a function of gamma in the mathematical sense, but we're just going to be evaluating it at the observed data that we have. But we're going to be evaluating it for all, or essentially all, possible values of gamma. And so you can just go through the process of doing expectation. You have to deal with the infinite summation, but that's not really a big deal. Anytime you have an infinite summation, if it converges, which in this case it does, it means almost all of those terms are approaching 0. So you can get a sum of an infinite number of things that converges to a finite value. Another interpretation for the denominator of Bayes' rule, which is what I think Rashika was alluding to, is you can think about, okay, I have a joint probability distribution for gamma, first roll of frame 1, second roll of frame 1, etc., all the way up to the first roll of frame 9, second roll of frame 9. So I have this big, kind of big, has 19 things in it, probability function for the probability that gamma is this or that, and x11 is this or that, and x12 is this or that, etc. So if I have this big joint probability mass function, the way we go from a joint to a marginal is by summing over the dimension that we want to get rid of, which in this case is gamma. We did this last Thursday for the simple case, you know, bowling first roll, second roll. If we want to get the probability mass function for the second roll, we have to take the joint probability of knocking down x1 and x2 pins on 2 rolls and sum it up over all the possibilities for the first roll, which was just summing down the columns of our 11 by 11 table whose cells contained the joint probability of knocking down x1 and x2 rows. And so when we did the marginalization, by summing down the columns, then we obtained this function for the probability of knocking down x2 pins on the second roll that didn't depend on x1 anymore. X1 did not enter into that function. And so if we take this joint probability mass function, which has one dimension that involves gamma, sum it over all possible values of gamma, or at least all the ones that are relevant, then what we're going to be left with is a marginal probability mass function that only depends on the x's, doesn't depend on gamma anymore because we summed it out. And that's the process that we have to go through. Now, a little bit more complicated, like I said, because there's an infinite sum here. But basically, the way in which you sort of computationally attack these infinite sums is you just start at 0, sum the things up, and when your contributions to the sum start getting so close to 0 that a computer can't even distinguish it from 0, then you can stop. And really, you know, in this case, you would stop before you even get to like 200, you know, most of the time. So everything from 200 to infinity, it's just going to be probability essentially 0. And so adding essentially 0 to this thing isn't going to change much. And so when you see an infinite sum in algebra, just think, okay, I'm going to sum this up until the terms get negligible and stop in my computer code. And we'll talk more about how to do things like that. So I think we will leave off for today. Had a few more slides that we didn't get through. We'll get to them at some later point in the semester. I am going to post the first homework assignment tonight. It will be due before class Thursday, and it will cover you know, the stuff that we've done up to today. And you'll need to turn that in on Canvas with R Markdown. And so if you're not familiar with how to deal with R Markdown files, be sure to either attend or, you know, watch the video, get the notes from somebody else, the extra session that Terry and Rui are going to do Monday morning. All right, so that's it for today.